expressions of SU2, and so just to remind you what we did. So we are going to use slightly different notation this time. So this is the usual JA notation, which I think all of you are familiar. So I keep applying J minus, and at some stage I will have Jn, and then Jn minus 1, all the way up to J minus J. Okay, and about coefficients. So this is all about J minus action. The coefficient that I pick up here, which I proved in this step, but here I said it without proof. It is this J plus M, J minus J plus 1. It's easy to do that by using the. So if this is normalized, and you apply the J minus operator to get here, then you can simply look at the norm of the state to figure out what coefficient to pick up. That is to say, when you apply J minus on this, it becomes this coefficient times that. Okay, and these are called the weights. So these are the J3 eigenvalues. So the J3 eigenvalues are J minus 1, This is M. This is N minus 1, all the way up to minus 3. Okay, and this was an irreducible representation. It was finite dimensional, and it was a unitary representation. Okay, in which I said that J plus and J minus were supposed to be Carnosian conjugates. In other words, Jx and Jy were supposed to be Carnosian operators. Okay, so that is what it was, and let me give you an example of quantum mechanics of a particle on a sphere. Okay, so there is a physics example, quantum mechanics of a particle on a sphere. Okay, how such things come about. By the way, I had mentioned, of course, that J can be 0, half, 1, or this possibility. Okay. Now, so in your quantum mechanics, what you do is to look at the angular momentum operator, which was classical value is R plus P, of course, and then when you quantized, it becomes minus I 8 bar times the derivative operator. So with all that, Lx will become y times z. So I'll write h bar equal to 1. Lz is equal to, or Ly, z, x, z. And x and y minus, I think the minuses, because this p, like px is equal to minus I. That's my convention. With this is what I get. Like that. Okay. So before going on to this quantum mechanics of a particle or a sphere, let me tell you some interesting fact, which is that consider a vector space of polynomials in x, y, z, okay, of degree. So this is polynomials No, this is just n. Okay. Now, I claim that Vn carries a representation of this. What does it mean? That when I apply, let's say by Lx on any element here, okay, I get back some element of say y. So let's say an example. N equal to 1. Well, first of all, n equal to 0 is constant. That of course is trivially thing because Lx, Ly, Lz, all of them kill it, and I get a 0. So that's a trivial representation. So this is a trivial representation. All of these guys give 0. N equal to 1. So now homogeneous polynomials in x, y, z. So it can be x, y, or z, and complex linear combination of these. Clearly, act by any one of these. What these guys are doing is these derivative operators are reducing the degree, and this is increasing the degree. Okay, so the final degree is remaining the same. Okay. So this clearly carries a representation, and you can act by Lx on these things to see what happens. We will actually use a somewhat more clever basis, that's x plus, x minus, and z. Okay, so in order to figure out about these. But the point is that you can take x, y, and z as possible basis elements in the sense that an arbitrary element of this vector space would be like ax plus by plus cz. Okay, and so then what this operator, Lx operator, will do is to take you to another linear combination of this. So therefore, these become matrices. Okay, so Lx, Ly, and Lz will become three-dimensional. Each of them will become three-dimensional matrices because this is a vector space with three basis elements: x, y, and z. Correct? Similarly, n equal to 2 can have x square, y square, z square, xy, yz, zx. Okay, and compressed linear combination of these things. So clearly, again, by the same story, so there appears to be 6 basis elements. Okay, and these fellows, okay, become like 6 by 6 matrices. Okay, except that there is this element which is x square plus y square plus z square. There is a particular combination which is x square plus y square plus z square. Okay, all of these guys, okay, simply annihilate that. So if you rearrange this basis in such a way that you have x, so this is what I'm saying. So this span is a 6-dimensional vector space. You can write that as the span of x square plus y square plus z square, which is a 1-dimensional thing, plus the rest, Okay, so you can take some other, you can rearrange the basis in such a way that this is one basis element and there are 5 other basis elements. Okay, now this is a reducible representation. Why? Because Lx, Ly, Lz acting on this, okay, just gives you 0. And Lx, Ly, Lz acting on this stuff will keep it within themselves. Okay, we'll soon see explicitly how that works out. Good, and so on. Okay, so when n is equal to 3, that is also a reducible representation because there will be factors like x squared plus y square plus z square times x, y, or z. Okay, such things. So, so in other words, let me say this. So when n is equal to 3, you might think that this x cube, y cube, z cube, blah blah blah, whatever number of basis elements it is, but out of this, there will be this that's an invariant combination. You might as well replace this by some r square. This object is a constant so far as these derivatives are concerned. Of course, because it's supposed to be rotation. Okay, so rotation operators don't do anything to these x square plus y square plus z square. So now of all the cubes, there will be these three kinds of cubes, which is this fellow. So this is like r square x, r square y, r square z. So from these elements, you can sift out these objects. Okay, so this will reproduce. This will exactly, repeat what happened for n equal to 1. Okay, so this representation will come back here, and the entire representation here will split into some irreducible representation and this n equal to 1 representation. Okay.
So sir, these three quantities, they should be dependent in some way, because this should furnish
I mean, I'm
us
saying
with
that you
seven-dimensional representation.
You rearrange this guy,
Okay.
okay, in such a way that you have.
So I mean, this three quantities and
Yeah.
this number of independent polynomials is 9,
Mhm.
and if we remove this 3, we end up with 6. But we should have 7, because n equals 0 gave us one-dimensional representation. N equals 1 give us
So yeah. So what is the counting here? What is the counting you?
3 into 3 into 3. That's 9. And I think one of them should be related to.
Yeah.
9 minus, and it should be 7. The total dimensionality of this representation should be.
So n equal to, so let's come to the L value of these things.
Yeah.
So then that would be clear. So n equal to 0. So this n object here, okay, it becomes the L value itself. Okay. So now today right now I'm talking about orbital angular momentum. Okay. So this is a J. This is actually J. I was using J here, but this is some kind of J. It's orbital angular momentum of this form, and it has this representation. So the corresponding small j value are called simply small l, as you all know from quantum mechanics. So this n turns out to be the same as L, and so therefore this is a trivial representation, L equal to 0. This is L equal to 1, and so therefore indeed it's true that. So remember, I should say here that the dimensionality of this representation is 2j plus 1, because there are 2j plus 1 number of basis vectors here. So 2l plus 1 is indeed 3, and 2 times 2 plus 1, that's 5. And how did that 5 come about? Because there was 6 here,
minus 1.
and 1 went out, so that's 5. Now this is 7, and your point is that
And this 3 cannot be independent, completely independent. That is 9. So we have
2
3
is
to.
2.
Oh, no, that's 27. 27. 27. Sorry. 27. And we are not in 20.
All of them are not in the time.
So basically, I'll tell you what this object. So this representation, which we'll come back to in greater detail, is that I have this n equal to 1 is this L equal to 1 representation. So that is the spin 1 representation. Okay. Here, what I am trying to do is to combine two spin 1 representations. Okay, because these are products of spin 1 objects. So x, y, and z each are spin 1 objects. Okay, and then I am taking a product of these. Okay, so spin 1 times spin 1. Okay, so that is yeah. So spin 1 times spin 1 have been 5 plus 3 plus 1. But this 3 appears only if you take antisymmetric combinations. Okay. Here there is only one particle. Okay. So therefore, all these guys in which x and y, they are antisymmetric. If there were things like x1, y1, z1 and x2, y2, z2, that's like 2 particles. Okay. Then I could take antisymmetric combination, but there is no antisymmetric combination here. Like xy minus yx does not appear. Okay. So therefore, this guy is gone.
What does this mean physically then? Like 3 cross 3 with the same XY?
Yeah, so this is 3 cross 3 with symmetrization. Because, so I'll actually come to this in great detail. Today's lecture is mainly about tensor product decomposition, and this will come. So just hold on for okay. So this is how the counting goes. Here, okay, this is 3 cross 3 cross 3. So to begin with, okay, you have these, but all symmetrized, okay. And so for instance, I could have 5 plus 3, 5 plus 1 here. Into 3, and I'll have to further symmetrize. Okay, so I'm saying something without proof, but I should really. So this is like spin 2 times spin 1. So I can have spin 3. Okay, so in terms of this spin notation, this is 2 plus 0 into 1. Okay, 2 into 1 gives me what? It can give me 3 plus. So this is the spin notation rather than the dimension notation. 3 plus 2 plus 1, that's it. That's coming from this product, and 0 times 1 is another one. Like this. Okay. So this, the dimensionality of this is 7, this is 5, and this is 3, and this is 3. Okay. Symmetrization has taken away some things here, and I believe that the further symmetrization of these, okay, will get rid of this one, get rid of this. Okay, I'm guessing how this might happen, but basically, what you should be left with are. What you should be left with eventually are some L equal to 3 and L equal to 1 representations.
Sir, it's actually consistent. I mean, this 3 things, because we can have 10 independent polynomial of this form, cubic.
Monomials.
Yeah. Of
10.
monomials. Yeah. X cube, y cube, z cube. That's one
so
of its.
Okay, so the counting was 10.
10. The counting was 10, right?
Yeah, so then it's 10.
10. 10
Yeah.
minus 3, then it's perfect.
Yeah. So then, yeah, that's right. So this 5 was 7, and this, yeah, it's 10. So the symmetrized combination is 10. And good. So if there are 10 fellows,
Yeah,
and you
10
take
fellows.
away, so everything is fine.
Yeah.
It was not 27.
Yeah.
And okay, good. So that's what it is. And
Many of the 27s are equal actually. X, X, Y and X, Y,
oh,
X.
yeah.
They're-
So you don't take those into account. So that will come if the X, Y and Z, these belong to different particles, and you can have possible anti-symmetrizations and symmetrizations and all kinds of things. But here no. Here they are X, Y, Z and so they are not like X1, Y2, Z3. Alright, so this is what it is. So therefore, homogeneous polynomials of degree n, they correspond to reducible representations in this way. So we just looked at some examples of these angular momentum operators, and here the angular momentum operators are orbital angular momentum. Okay, everybody, is this clear? So for instance, in this could have been this n equal to 2 would have meant that these are 6 by 6 matrices, but their structure will be that there will be one block here, 1 by 1 block, which will be 0. All the x, y, Lx, Ly, Lz, everybody will be 0, and there will be some mixing here, some 5 by 5 stuff, and that will correspond to L equal to 2, and this L equal to 0. And similarly here, for N equal to 2, which is the same as L equal to 3, so the way it appears is that it will have L equal to 3 and L equal to 1, these blocks. So this is some 7 by 7 block here, and this is by 3 by 3 blocks. So overall, these are some 10 by 10 matrices, which will give rise to the reducible representation. Okay, alright. That is actually, so now we will go back to the problem that we wanted to do, that is the quantum mechanics of a particle on a sphere, and after that we will also talk about quantum mechanics of a particle in a central force. So these are all prime examples of okay, so now as I said that let us use some more clever basis, which is this x plus minus I y, and with this the expressions for j plus and j minus and all that stuff, they become the following. So here you should check these expressions. So these become, according to my calculations, these become z del minus plus minus x plus minus del z, and jz becomes x plus del plus minus x minus del minus. Okay. Now let us. So we are using complex linear combinations here. It's a complex vector space. So clearly, I can choose my basis in such a way that this n equal to 1 vector space is now spanned by x plus, z, and x minus. These are my three new basis elements. Okay. And now, if you apply j plus on this guy, okay, you find that it is 0. So all these j's are actually, okay, every j is actually L here. We are talking about orbital improvement. So the j's are L's. Okay. So j plus acting on this gives you 0. Everybody agrees with me? Because the derivatives in j plus are del minus or del z. So therefore, this is annihilated. Okay. So this must be the highest weight state, right? So last time remember that we have it here. So use it for j equal to 1. Okay. So this guy, when you act, so by the way, so I'm coming down like that in j minus, and I'm going up like that in j plus. So j plus acting on this gives you 0. So this, therefore, we identify this with 1, 1. Okay. So that's the highest weight state. It's annihilated by j plus. Similarly, this guy is annihilated by j minus. That again you can check. J minus has an L plus operator, Lz operator. So this is, so therefore this is 1 minus 1 and z. How do you know what z is? So you have to, so in order to, so the obvious identification is that z should be 1, 0. But how do you know? So by j minus operation on x plus, it should come here. Okay, so let's try that. So j minus is z del plus. That will act here. That will give you z. No doubt. Shall I do this? So I'm claiming that should give you a z. Sorry, 1. J minus, excuse me. G minus acting on 1 1, does it give you a Z or not? Okay. G minus is Z del plus minus x minus del Z, and 1 1 we have identified already to be x plus. X plus. So let's apply that. So Z del plus acting on x plus gives you Z. Done. So indeed this identification is correct. Okay. And now you can see that these objects, which are all living on a sphere. Now let us say that x, y and z, these coordinates are living on a sphere. Okay, that is why I have used capital R square here rather than small r square. Let us say that all these x, y, z's are living on a sphere, okay, of capital R radius. Then clearly all these guys have an action on these things anyway, right? So therefore, and let us say this R, capital R is 1. What I am trying to say is the following, that I am using the same idea that these are homogeneous polynomials of degree n, except that I am also using a restriction that x square plus y square plus z square is equal to 1. Okay, no problem at all on these things, because these they still preserve this one as I know. This radius is not changed by the angular momentum operators. So now this is of course by the usual spherical polar coordinates. This becomes x plus is sine theta cos phi plus I sine theta sine phi. So that's sine theta e to the power I phi, and that you can recognize as the spherical harmonic number y100. Okay, so this is how spherical harmonics appear in fact. Z is equal to cos theta, so that is y10. Okay, and x minus is equal to sine theta e to the power minus phi, so that is y1 minus phi. Now, these functions, if you take linear combinations of these functions, okay, you can again form a vector space. Okay. You can't form a vector space out of x plus z and x themselves, but now if you think of these as wave functions, okay, you can construct independent linear combinations of this, this and that. Okay. So that's a vector space. So is this clear? What I'm trying to say is that from the fact that x plus z, this combination x plus z and x minus, okay, carried a representation of the angular momentum algebra, I have arrived at this result that these guys carry a representation of the angular momentum algebra. Once I have arrived at this result, I can forget about how this came. In particular, the fact that there was a quadratic restriction on this, I can forget about that.
X plus z and x minus, those were the new basis elements, new basis elements for the.
Okay, so I am saying two things. First of all, when I think of these as polynomials, okay, there is no restriction on them at all. Okay, so now. So let us say, okay, instead of saying all this, let me keep this. Okay. Now everybody is happy with me. Okay, right? R sin theta, blah blah, etc. etc. So this will be R times this, R times this, R times this. No doubt that if I don't put any restriction like R equal to 1, no doubt that this acts on this to sort of rotate these among themselves. Okay. Now, for a particle on a sphere, I can take these, okay, as my wave functions or functions. Okay, these are some functions on the sphere. Okay, and I can even put some Hilbert space structure on this. Okay, I can take any one of these guys. Okay, psi theta phi whole small square and multiply, which is the measure sine theta d theta d phi. Okay, with that, this becomes a Hilbert space. And then, just like I said, these carried a representation L equal to 1 representation. This carries an L equal to 1 representation. Basically, I am saying the same thing, except that it gives me, for free, the expressions for the harmonic spherical harmonics.
So, but it means in terms of the polynomial, it's some very weird kind of vector space coset kind of thing. What is that in terms of this polynomial?
What is that in terms of these guys? Now they have become functions.
No, no. In the polynomial side, if you look,
Yes.
then once you have decided that x square plus y square plus z square equal to 1, then some of the polynomials will be
No. When I'm thinking of polynomials, I'm not putting this restriction at all. No, this, they remain, so only thing that happens from the point of view of representation theory, okay, they just get split as represented. They remain vector spaces. Here, I'm not saying that x square plus y square plus z square equal to 1. That would be wrong.
that is
X square plus y square plus z square is a special vector.
yeah.
I keep it separately.
Yeah, from polynomial point of view, it is very weird, yes.
Very
Very weird. Because then x times x square plus y square plus z square becomes x. Very weird.
Oh, I see what you mean. No. These, if you have 6 coefficients here, okay, these 6 coefficients you can write as some coefficient times this, plus some 5 other coefficients times that, and these 1 and 5 coefficients can be uniquely related to the 6 coefficients here. Okay, alright. So,
Sir?
what? Yes.
So you maybe I got it wrong. Did you just say that x plus z and x minus do not form a vector space?
X plus z and x minus, of course, they do form.
They do form a vector.
Yeah.
Okay.
So you have the general function, which is like a plus x plus, a minus x minus, and whatever some b z. This is your general polynomial. Okay, and this of course is related to some ax plus by plus c. Okay, or b c by plus b. Okay.
Now you're saying with the constraint, even the YLMs will form a vector space of their own.
YLMs form a vector space in a different way. Okay. Now I can assign some Hilbert space structure. Okay, which is like now a some a y11 plus b y10 plus c y1 minus 1. From the fact that y11, y10 and y1 minus 1, okay, they are rotated among each other, okay, by this construction, by the angular momentum operators, I know that this is a vector space which carries a representation. But this fellow does not have the interpretation of being a point on the sphere. Okay, that's the point that I'm trying to make. You can now take linear combinations of these guys, but they would not be points on the sphere. Okay, because a sphere is not a vector space. That's what we said in the first thing. But I can take linear combinations of these guys, in particular complex linear combination of these guys, and that would form a vector space in its own right, and would also carry a representation of the angular momentum algebra, because by this analysis we have said that if you act by L minus, then this comes here, and if you act by further one L minus, it acts here, and the L pluses will take you up there. Okay, and for example, if you look at, in fact, so in terms of the spherical polar coordinates, you can write all of these guys, okay, in terms of spherical polar coordinates, and in particular, as you know, Lz, okay, just becomes I del phi. Okay, and you know there are expressions for L plus and L minus which you can write down. You can find out from Wikipedia, and so clearly Lz, okay, has the value when you add this on that minus. This will give you 1 because there is an e to the power I phi here. There's no phi here, so that is Lz equal to 0, and this is okay. So it's you know it's a cool way of getting spherical harmonics, and in fact this works not just for S2. Okay, it works for other higher dimensional counterparts of this exercise also. So you can have spherical harmonics on S3, you know, by methods which are similar to this. So this method actually is more general than what that's. Perhaps we will come to something in the nature of the homework. Okay, so good. Let me leave this thing here. So therefore now I didn't quite say how to. So you got some you know nice Hilbert space with a nice basis, okay, and let us say that the you know Hamiltonian for the particle on a sphere, okay, is just the invariant Hamiltonian. What's an invariant Hamiltonian for a particle on a sphere? Okay. So you can start from particle on a, let's say a free particle on three dimensions, okay, and write it in spherical polar coordinates. So what happens then? Anybody remembers what happens? The Hamiltonian for a free particle in spherical polar coordinates. So it's just some stuff like this, minus 1 squared, L square or something, minus or plus or something like that. And if you also add some central force, then there is some P of R. This L square here is the quadratic Casimir. What does it mean? That means that this L square is Lx square plus Ly square plus Lz square. This by itself could be the Hamiltonian for a particle on a sphere, okay, which is rotationally invariant. The Hamiltonian for a particle on a sphere obviously, you know, naturally will involve Lx, Ly and Lz because those are the momentum operators. And the invariant combination, there is only one invariant combination. Okay? It's called the Casimir. So the notion of quadratic Casimirs will keep coming back to. Okay, that's there in other Lie algebras as well. And you know, semi-simple Lie algebras will have the notion of the quadratic Casimir. Okay, good. So I think we're done. So with this technology, the way you can construct nice wave functions of the entire Hamiltonian, including the R dependence, would be of the following kind, that you already know. So it will be like that, and it can have some you know, so you can do separation of variable, and it can have some other function f, let's say, of R. And you know, if you look at the Hamiltonian, this L square, okay, so there are some things which I guess everybody knows. So if you if you evaluate this L square on the spin L representation, or if you evaluate J square on the spin J representation, then what does it become? J into J plus 1. So generally speaking, J square acting on any Jn. So that just follows from what we did last time. This is J into J plus 1. Okay, so this operator is the same throughout and its representation and is given by j into j plus 1. So for the angular momentum operator it's L into L plus 1, and so for this it becomes L into L plus 1. I think it's a plus L into L plus 1. Okay. So now there's a radial operator which depends on L. Okay. So therefore you have to now solve the eigenvalue problem of that. So clearly that will involve some L here, okay, and if this V itself is a sort of bounded potential, then you can have some further quantum number coming from this problem, okay, such as in the hydrogen atom, and then there is some additional label here. Okay, so the entire Hilbert space for the particle, okay, in the presence of a central force will become split into something coming from the n guy. Okay, so you know the structure, how it goes. It's like for the hydrogen atom, it's 1s, 2s, you have a 1 by 1 representation, then 2px plus iy, 2px minus iy. Okay, whatever, the 2p guys. So that's a 3 by 3 representation. Okay, and then there is 3s, 3p, etc. So this is how the entire Hilbert space for a particle, for the electron in the hydrogen atom, it has the structure of a reducible representation in which this part is 1 by 1, this is 1 by 1, this is 3 by 3, etc. Okay? So that's a huge, humongous reducible representation. Okay, so now, so that's a sort of simple example. Basically from this we should just take away from, oh I forgot. So the generalization of this, okay, is fairly easy. Okay, so what do you do for n equal to 2? For n equal to 2, clearly the following basis is available: x plus square, x plus z, then z square, and then the z x minus and x minus. Okay. This again is clearly the high spread state. Okay, because the x plus square is annihilated by j plus because it has only the wrong kind of derivatives. So this will correspond to 2, 2. This will correspond to 2, 1 because you can arrive at this by this way. The z square, I forgot whether it's z square or some combination of z square and x plus x minus.
I think x plus x minus would be the other state because it's annihilated by both sides.
So it's just plain z square, isn't it? Ah, I got it. So it's z square minus x plus x minus. So if you keep applying your j minus operator as it appears here, these are the things that you generate. Okay? Not z square plus x minus. That of course is the invariant combination. So that gets separated out. Okay? So this corresponds to 2, 0. This corresponds to 2 minus 1, and this corresponds to 2 minus 2, and these duly also, you should check this. So indeed these correspond to the spherical harmonics. So all spherical harmonics, okay, can be easily obtained this way. Particularly the highest rate spherical harmonics is very easy to do. It's always some x plus to the power n. Okay, and similarly the lowest guy. You can start having mixing from here onwards. All right. So that's the story of violence as representation. So it says various things. So first of all, how these operators act on these guys. Okay, we use some abstract, Lie algebra notion to arrive at this representation, just the commutation algebra. Here we have a derivative representation of this operators. Okay, so the operators can, acting on a Hilbert space, can appear in various different ways. So here it was a derivative. Okay, and in particular in this entire big Hilbert space, which I wrote, it's an infinite dimensional matrix. So okay, so this Lx, Ly, and Lz, okay, can be thought of as infinite dimensional matrices. These matrices split up, okay, into these blocks, and those are the reducible representations. Okay. Now we will quickly go to the main point of today, which is how to compute the tensor product of two representations. Okay. So I'll start with the simplest thing here, which is that I will take two representations, so spin J1 and spin J2, and I will, so I presume everybody is familiar with this quantum mechanical notations, right? So I'll keep taking these objects, okay, for fixed J1 and J2. So I will take the linear combinations of this, where M1 and M2 can be in their entire range. So that is to say, M1 will go all the way from minus J1 to J1, and M2 will go all the way from minus J2 to J2. Okay. And just as we were doing here in terms of the homogeneous polynomials, we will try to see if there are reducible blocks in these, okay, and how to exactly find those reducible blocks quantitatively. Okay. Yes.
So regarding the previous thing, like the L's have an infinite dimensional representation.
Yes.
So if you look at n equal to 1, you have a one block,
Right.
single block. If you look at n equal to 2, it splits up further, right?
Into some 5 by 5.
One
Yeah.
plus
So
one plus
it was 6 by 6, and then it
Yeah.
was,
So
yeah.
right. So but the n equal to 2 representations require the 1 plus 5 the entire that block.
Indeed.
So how do you, like, looking at the matrix? Can you, like, if even though they split up into, like,
How do
you
I
look at-
know that it's getting split up?
Yeah, how do you know that each block does not correspond to a so each block corresponds to a reducible representation,
Right.
irreducible representation.
Yeah.
But some of them add up to good reducible representations. Like for example, if you look at n equal to 2,
Yes.
those reducible representations specifically need a 1 plus 5 sort of block.
So here it is. So these were the 5 basis elements which I wrote down here, but there is another one here, okay, which is x square plus x minus. Now clearly you can separate out these guys and this guy. Why? Because Lx plus L, Lx, Ly, Lz acting on this just leaves it within this space, namely 0. Okay, and here, L minuses take you down, L pluses take you up, and these are all eigenstates of L3. So clearly it's an irreducible representation. If it so happens that L minus takes you up to here, okay, and then some further action starts from here, then it will split up. But that's not happening. L minus takes you all the way down from here to here. So that's irreducible.
Right. Okay, I'll ask you the question.
Okay. Good. So now we'll do a similar exercise with this lot. Okay. So this guy with this entire range of this, and we'll see what. So this is what kind of reducible blocks. No, they're splitting. Okay, that's the game. So we'll do the simplest. What's the simplest? J1 and J2 are both equal and half. Okay, that's what we do. J1 equal to half and J2 equal to half. How many states are there? So in the J1 there are 2, and in that one there are 2. So 4 states altogether. So let me write it down. Half, half, By the way, in this list, how many vectors are there in this list? As many M1 M2 pairs. Okay, so that's 2j plus 1 into 2j1 plus 1 into 2j2 plus 1, correct? So we want to know how these guys split into ellipse. Okay. Good. So I wrote one, and I'm writing another one here. So this way, half minus half, and so yeah, okay. So just for simplicity, these are the J values. Nothing is happening to them. Okay. So I might as well forget about the J values. J1 and J2 I can just get rid of. So this is half half. Minus half half. Half minus half. And minus half minus 33 by 2. Okay, so I have written it in the form of a diamond. Okay, there is a reason for that. But anyway, so there I have written all the 4 states. In what shape I write them is my concern. Now I claim that this object, okay, is a high state state. How? So let me go back to the representation of to the definition of how Lie algebras act on tensor products, tensor product states. This I think I have said before, but let me say it again. So suppose that I have some Lie algebra element. Let me call it x. Okay, x. When it acts on AB, how does it act? Okay, this AB is a tensor B. Okay, so this is don't write this tensor product notation now. So this, by definition, is XA B plus A X B. This is how it is. How does it follow? Okay, remember that e to the power tx is supposed to be a group element. Now that acting on a tensor product state, this we have explained before, that it acts on this and acts on that. So it is e to the power tx acting on A, tensor product of e to the power tx acting on B. Now let us take t to be smaller. So then this is 1 plus tx. So this is A plus t xa and b plus t x b, and keep only up to linear order in t. Okay. You get xa b plus a x. So what I get is that 1 plus t x ab is this. Now 1 acting on AB just cancels this one out. Okay. So this 1 acting on AB just cancels this out. So I have, and now I have t appearing in both places, so cancel out t. What you get with this? Basically it's Leibniz rule. So Lie algebra elements act by Leibniz rule. Okay. So it acts here first and so on. If you have A, B, C, D, etc., it again acts by Leibniz rule. Okay. Of course, if there are, if there are fermionic operators, blah blah, etc., then you have to, by taking it across, you may have to bother about signs. Well, we don't bother about that here. Okay, good. Now I claim, with that definition, this is annihilated by J class. J3 on this. J3 acting on half. I apply Leibniz rule. So J3 acting on this half gives me a half. Okay, and J3 acting on this half gives me another half. So this therefore is 1 times half. Okay, so this therefore has a weight, which is a fancy name for J3 eigenvalue, which is 1. So the J3 values are listed here is 1, 0, minus 1. 0 is clear for any one of these states. So it will pick up minus half from here, plus half from here, so it's 0, etc. So just like this rule. Okay, so these are the ways. Now I claim that J plus acting on this 0. So that's clear. J plus acts this by Leibniz rule, so J plus acting on half. Remember this was half. Okay, I have not written the half, but G plus acting on half by definition is 0. So it's 0 on this, 0 on that, so it's 0 altogether. Okay, so therefore it's the highest weight state clearly with weight 1. So what is this state then? 1, 1. Very good. So this state therefore should be represented as 1, 1. Very good. Now there are of course 2 blocks here. Okay, so there's a 2-dimensional space with weight 0. Okay. Now, okay. So similarly, this object is the lowest weight state. Okay, and the spin is minus 1. So therefore, again it's 1, minus 1. What's happening in the middle? Any idea what's happening in the middle?
1, 0, 0,
Yes.
0.
Actually, understand this part,
You didn't understand the logic of this?
So, firstly, the operator acts on this tensor product space like this. And the same operator e to the power tx, which has the form of the x, right?
E to the power tx is a no. E to the power tx is a group element.
It's a group element, but
Yeah.
the form of this is basically matrix representation, right? X is also matrix representation, and e to the power tx is basically 1 plus tx plus tx whole square, and this. So this is the same operator, the same kind of operator, and acting on the tensor product space, and it acts differently than the former one.
The notion of x, okay, how x acts on this is really to be done by taking this minus a b divided by t and taking the limit. This is how x's act. X's really act by derivatives. These x's, in terms of the geometry, which I never explained but briefly alluded to, is that these x's correspond to tangent vectors, and e to the power tx corresponds to group elements. So they do act differently.
No, they do act differently, but in the matrix representation, what you taught in the
So this is
last
the real
class, I
thing.
think, they act similarly.
This is the real thing. This is the
This
true
is the
statement.
abstract.
There is a true statement that groups act on this like that, but from there you can find out the derivative. Okay, in the sense that this e to the power, so e to the power tx minus ab divided by t and limit. This is the definition of the action of x on a. This is just a definition. Okay. This animal is called a derivation. More abstract. But this is yes.
So when we always write like actions of operators on such tensor products like in the first line, we
Yeah.
implicitly take this into account that this is in the case of infinitesimal parameter of the group.
Indeed. So it is the t square, t cube, etc. those terms which correct it to give you back this one.
the chance of the manipulating the symbols.
Yes. That.
So if I am writing some sort of a matrix representation of the second line,
Mhm.
this tensor product state AB
Yes.
is like the square dimension of just A, right? I mean, let's say half of it, I take this half of example. A
Yes.
is a two-dimensional space, B is a two-dimensional.
That's correct.
E to the power tx
Mhm.
will have the same will have
So this is a four-dimensional object now.
yeah.
Yeah.
And
So e to the power tx acting on a four-dimensional object will give you a four-dimensional object.
No, I mean,
So
that
what is
x
the
corresponds to,
Just-
okay, yeah.
What is the dimension of e to the power tx here?
E to the power tx here is, so representation wise, it's a 4x4 matrix.
Okay, and so that's what I'm saying. So on the right hand side, it becomes a two-dimensional.
Yeah. So there's first of all something is abstract.
Yeah.
This e to the power tx here, okay, is an abstract group element, really speaking. Okay. But when it acts on these, this EI, EJ fellows, EI, EJ. So basically, I can even think of this as AI. But let's say that these are EI, F, like that. Then acting on this, e to the power tx of course has some matrix representation. It just mixes up these basis elements into linear combination of such things. So in that way, this x gets a 2j 1 plus 1 into 2j 2 plus 1 matrix structure, dimensional matrix structure. And then of course the point is that these guys split up. Even the group elements split up into blocks. Okay? So we are doing everything in terms of infinitesimals because that's easier.
No, I mean, the one on the left hand side is a 4x4 matrix. It would be, if we think of matrix representation.
Indeed.
And those on the right hand side are 2x2, 2x2.
Ah, yes.
That's what
I see.
was
Good.
Yeah.
Good. Thanks for yeah. So this is an abuse of notation. Okay. So what I should really have said is that
Tensor
thank you. I see. I really get it. Yeah. So it's indeed that's correct. Yeah. Okay. So is this clear to everybody? I mean, it's a four-dimensional representation really. This is this abuse of notation in which the abstractly algebra element and this representation are given the same symbol. But actually you are right. This is a four-dimensional representation, this is a two-dimensional. Absolutely correct. Okay, and this game is happening here too. Okay,
Yeah.
when I say that J plus, okay, the J plus for this, okay, is different from the J plus for this because this J plus is acting on this guy. Okay, that's a 2 by 2 J plus. Okay, that's actually the Pauli sigma matrix sigma plus. Okay, and so on. But this is actually genuine J plus. Okay, this J plus turns out to be a 3 by 3 thing. Okay, the big J's here in principle are 4 by 4, but they further split up into this. So this is okay. Thanks for pointing that out. Okay. So now we have a problem here, namely that very nicely I would have gone on from here to here to here. Okay, but there are two troubles here. What do I do? Check for the capital J3 doesn't distinguish between this and that.
I mean, sector Casimir offered
Capital
J square.
Much simpler. I just apply by J minus and I'll see where I land.
What you meant.
So I'll land at some particular linear combination of this and this. Namely what?
Symmetry and
So remember that by this rule here, by this thing here, when the two-dimensional J minus acts on half, it gives you 1 over square root of 2 times minus half. So let me just write that thing down. So two-dimensional representation of J minus acting on half. So this is of course a lazy way of, so this half is actually half, and that gives you 1 over square root of 2 2 times I got square root of j, didn't I? Last time. So what's happening? If m is equal to j, then this is j plus j, yeah, square root of j. So if it acts on the jj state, then I'll pick up square root of j, and that's 1 over square root of 2. Okay? So
That's a
this.
D4, right?
Hmm?
And that
No. So let me go back to this notation. So the lazy notation. The lazy notation is the following. That d2
Okay.
of this gives you minus 1.
Yeah.
Okay. Now if there are two such blocks, okay, then I have, so let me do this once very carefully so that everybody is with me. So I'll do this step, okay, because that's an important step. So d4, I want to find out how d4 acts on this. Half. So this, by definition, is d2 acting on half and half plus half and d2. Jesus Christ. Something. Half. Okay. Now I have just, excuse me, d4 of anything. But now I am doing d4 of j minus. This is d2 of j minus and d2 of j minus. But I have just written the formula for d2 of j minus. So this guy from this master list is 1 over square root of 2 half. There, this is minus half now, minus half, and this half remains, of course, because it's Leibniz rule. And now this half remains, and this becomes 1 over square root of 2, which I can shift here. 1 over square root of 2 minus half. Okay? So this is, of course, your familiar statement of, down, up, plus up, down. So that's a symmetric combination. Okay? And this 1 over square root of 2 is also nice. So we are doing something right because this is normalized correctly. Therefore, the combination that really corresponds to 1, 0. And from this point of view, we remember that we have already identified this to be 1, 1. So, and it will also turn out to be the 3-dimensional representation eventually. Okay, so that's, I'm just making a little leap of faith here. Okay, so this guy, whatever representation it is, acting on this 1, 1, where will it take me? 1, 0. Very good. So this must be therefore identifiable with 1, 0. So the plus combination is identified with the square root of minus 2. That is the one identified with 1, 0. But then there's something left over. Okay? Namely, the leftover thing I can choose to be orthogonal to this. Now I'll prove for you why that is actually forced on me. Okay? But at the moment, let me choose the other guy to be orthogonal to this. So this one is used up, it's 1, 0. So I have nicely got 3 states which form an L equal to 1 representation. What is left over here is the minus combination of this. Okay? So I got, and I'll choose some representation, I'll choose some convention such that this comes with a plus and this comes with a minus. So anyway, so this is like half, doesn't matter really, but some sign convention you have to be consistent with. So this is basically the orthogonal state with some choice of sign. There is an orthogonal state. This is what? How do I identify what the hell this is? I can act by, even square knowledge. I can act by j plus on this, I'll get 0. I can act by j minus on this, I'll get 0. Is that clear?
This is both the highest and lowest fit statement.
Exactly. So
You can
what
directly act on JZ, right?
I can act on JZ, that I know.
Yeah.
JZ
That
was
was
zero.
zero.
That does not distinguish between this combination and the minus combination. See, the point is that only tells me that it is of the form j comma 0. That's all it tells me. It doesn't tell me what the j is. So I have found that this j comma 0 object here, this combination is j equal to 1, and this combination will turn out to be 0. So this will be 0 comma 0 y, because acting on this by j plus and j minus both annihilate. Okay. Shall we do this?
This
Sort of
is
clear?
so
If you act by j plus, this becomes plus plus, and this also becomes plus plus. So plus plus minus plus plus is killed. If you act by j minus cannot act on this one, because j minus can not really act only on this. So it will be minus half minus half minus minus half minus half. Done. So this is the guy which is, so therefore now we have proved that this is what happens, that so this 1 0 perp, that object is actually 0.
So, but we could have started with this thing, because total j equal to 1 and total j equal to 0, they will have to be orthogonal, right? So, once we have found the 1 0 state, you can directly claim the 1 perpendicular to it, we have to do 0 0.
Why 0 0? It is something else, but why 0 0?
But it will have to have j equal to 0, total j equal to 0.
Why? Why? Without using the j plus j minus test, how do you know that the total j has to be 0?
So, the total is either 1 or 0.
No. That is something that we are arriving at. That knowledge is unknown to us. Okay, that we don't know. The fact that half cross half gives you 1 plus 0. Okay. So what are the two things that we learn from here? Okay. So first of all, it tells you exactly what the linear combinations are. Okay. So namely, if you take the tensor product states, okay, this is a particular combination of the 4 tensor product states that gives you 1 1, 1 0, 1 minus 1. We found the coefficients. These are called Klebsch-Gordon coefficients. Okay. We'll do one more non-trivial exercise. This is too fast. No, actually I have 7 minutes. I have 7 minutes.
This last statement, so you know that we established that this vector 1 0 perpendicular, it spans an entire vector space.
That's right. That was the only thing that was remaining.
But to set up, but to call it 0 0, we still need the action of j
That's what we
squared.
did. So we took this. I don't know what the hell this is. I only know that the jz of acting on this is
So
equal
we
to
still
0.
need to do j squared on this.
No.
Okay.
All I need to say is that act by j plus.
Okay.
You find that is 0. What does it mean? That's the
Oh,
highest
okay,
weight
sorry.
state
Right.
with weight equal to 0.
Okay.
So that means j has to be equal to 0. Okay.
Equivalently, could we have just acted by j minus and not by j plus but j square? That would also be a possibility.
Everybody loves Casimir. But I'm saying, even without the knowledge of Casimir, just from what I did last time, okay, you can just act only by j plus. Okay. That itself tells you that it's a highest weight state and the weight is 0. So therefore the j value has to be 0. Okay. The fact that j minus also annihilates it is a good check. Okay. But you don't need to do it. Okay. Now, let me do this exercise. Oh Lord. let's say higher dimensional tensor product representations. So let's say 1 cross 1, spin 1 cross spin 1. Okay. So what? So now I'll take J1 equal to J2 equal to 1. Okay. So again, this will be a high squared state because the three-dimensional representation of J plus acting on this annihilates, acting on this also annihilates. So you're done. So therefore, overall J plus also is 0. Okay. Now the J3 value of this one. So let me write the diamond first. Okay. So this is 0, 1, 0, and this will be 0, 0. So let me say that this this is 0, 0, and 0, 0 can also appear from here, and when J minus acts on this, so it can give you two products by Leibniz rule. One is this, the other one is 0. I'm missing something. Oh, excuse me. This does not give you 0. Excuse me. Thank you. Minus 1, 1. It can give you 0, 0. So from here, so let me write it in the middle. 0, 0. And this gives you
1 minus 1.
1 minus 1, thank you. 1 minus 1. And then this guy gives you 1 minus.
No,
What?
whatever
Oh,
you
excuse
have
me.
written
Minus
on the
1.
left was fine.
Minus 1. Minus 1, 1. And 1 minus. Okay. At the next step, okay, J minus will give you two products. Okay. One is something which acts on this, that part is 0. So that makes the whole thing 0. And the other product of J minus from here is minus 1, 0. So that's minus 1, 0. But minus 1, 0 can also come from here. Like that. Okay. Similarly, J minus acting on this guy has two products. One is that annihilates this, so that's 0. And this animal gives you 0, minus 1, like that. And let me write this way. And here, what happens is that J minus acting on this. Yeah. Okay. And then again, this goes to 0. The other product is minus 1, minus 1, minus 1, minus 1. It's like that. And this is 0. Okay. So the counting is correct. So 1 plus 2 plus 3 plus 2 plus 1. How much is that? 9. Excellent. So we have an 9-dimensional Hilbert space. Now again, if you start from here, J minus will just go through like a bullet. Okay? It will pick out one fellow from here, one fellow from here, one fellow from here, one fellow from here. That much is clear. Okay? So again, for instance, here, one particular linear combination will be picked out by the J minus operation on that, namely the plus combination. Okay. So the orthogonal chap, okay, can be taken to be the minus combination. What will that be? Why? Very good. So I'll apply the J plus check on that. So if I have the minus combination and I act on that by J plus, okay, what will happen? This will be clean, nothing will, so I'll get 1, 1, minus 1, 1. So therefore, the minus combination, so what all do I get? So first of all, this guy is clearly, by the same logic, is It's the highest weight state with spin 2, with weight 2. So therefore, it is 2, 2. Here was the class combination we identified with 2, 1. And then this minus is another highest weight state with weight 1. So therefore, it is 1, 1. That's 1, 1. Once I have got a 1, 1, now I can apply this 1, 1 and that will go straight through like another bullet. So there's one trajectory going like this, another trajectory going like this, and okay. So I had 3 to begin with. So the j minus square acting on this will pick up some combination here, and then from the minus guy, j minus will pick up some other combination. Fortunately, there is only one thing left. Okay. Again, so this is something with the m value equal to 0. Okay. So what is the j value? Why? Again, just use the same logic. Okay, the j plus and j minus both should be equal to 0, and you carry on. So the this fellow does not propagate too much; it propagates up to here. So there is no problem. And this guy can propagate all the way up to here. So this is clearly 2 minus 2. Okay, so you really get it that there are 3 irreducible representations in this, namely. You get the j equal to 2 guy, j equal to 2, j equal to 1, and j equal to 0. But it's more than that. We actually got the actual linear combination coefficient, which I didn't do for this. You have to keep using this. Okay. Once you do that, you get what particular linear combination of these 9 basis states gives you these Jn states here. Okay. So more generally, this thing is called. So what I get is that I get some. So I begin with J1 M1 and J2 M2. Okay, and some particular linear combination of these things. Okay, so this is basically. What is the linear combination? The linear combination is J1 M1 J2 M2 and let me see. There's some particular linear combination, and the sum is taken over the entire range of M1 and M2 to give me this state. So I begin with, I start with all the 2j1 plus 1 times 2j2 plus 2 combinations, and I multiply them by some coefficients. Okay, and I get here a particular Jm, and these objects are called Lebesgue-Gordon coefficients. These are important coefficients. Lebesgue-Gordon. In fact, there is something which is very related to this, which is the following concept. That suppose you have a tensor product of 3 states. Okay, namely, you take. So in some very simple examples, we computed what the Lebesgue-Gordon coefficients are. Is that clear to everybody? Okay. And so I'll write down next time. So if you look at Landau-Lifshitz, the section called Landau-Lifshitz quantum mechanics, the section called addition of angular momentum. Okay. The Lebesgue-Gordon coefficients are explicitly written there. Explicitly. It's amazing. Okay, but it's explicitly. And so let me tell you the related concept. The related concept is the following: that suppose you have J1 M1. Now I'm talking about tensor product of 3 representations. Okay, J2 M2 and Jm. And you ask yourself, what linear combination of these things give me 0, 0? Gives me 0, 0. It can happen, right?
In Z direction.
Right. So, for example, m of course has to be minus m1, m plus m1 plus m2 has to be equal to 0. And it turns out that j1, j2 and j have to be the sides of a triangle. Okay? It comes by repeatedly applying this rule that the resultant angular momentum goes from j1 minus j2 to j1 plus j2. That actually is a triangle rule. Okay? If you think about it, j having the range from j1 minus j2 to j1 plus j2 is actually the same statement that j1 and j2 are sides of a triangle. Okay? Good. So of course okay, good. So now these things have a name, and let me write down the symbol correctly. Indeed, these are called Wigner 3J symbols. Okay, very simple. Let me make it democratic. J1, J2, J3, and M1, M2, M3. So the drill is the same. You look at tensor product of this. You can split them into reducible blocks. Somewhere along the line, you will find a 0, 0 state. Okay? Where? So if you take all these guys, 2j plus 2j1 plus 1, j2 plus 1 times 2j3 plus 1, all these vectors, take a particular linear combination of them, okay, you will get a 0, 0. So the sum here is supposed to be the entire range. Whatever is allowed by the restrictions that I have said. This object is a singlet. Okay? This, if this is true, you can more or less see that this guy and that guy, okay, should be related. Okay? To use a particle physics analogy, what we are doing here, 3 particles are coming in and forming a singlet. Okay? 3 particles, can they annihilate each other? How can they annihilate each other? Of course, only when their total quantum numbers just become 0 overall. Okay? So this statement here, forming a singlet out of 3 different representations, is like this. Can these 3 irreducible representations annihilate each other? And what's Clebsch-Gordon? Clebsch-Gordon is this. That J1 M1, J2 M2, okay, can it give rise to J3 M3? Okay. So it's the same S matrix element, you know, except that there are some phase factors between them. So the Clebsch-Gordon is related to the Wigner, by the way, so this is called Wigner 3J symbol. Okay, and these guys are related. These guys are related by. So let me use the notation thing. So this is related by. Let me keep it Jm. Then this minus 1 to the power j1 minus j2 you can derive it, it's not that big a deal. Just some normalization and times the j m1 m2 minus m. Okay, so this is the relation between Wigner 3J symbols and Clebsch-Gordon coefficient. Is that clear what I'm trying to say? 2 J1 M1 and J2 M2 particles are coming and they're giving rise to a JM1, right? That's what we're doing. We're trying to figure out what linear combination of such this J1 M1 J2 M2 guys gives rise to JM. But if I flip the arrows of that reaction, okay, it just says that, you know, what is the linear combination that I should take, of the various polarizations, so to say, of these particles, J1, M1, J2, M2 and J3, M3, so that I get an N equation. Okay? But except in flipping those things and so on and so forth, I pick up some signs and some factors. Okay? So, but it's proved in Lagrangian glitches, like everything on earth is proved in Lagrangian. So that's what it is. Okay. So I think that sort of is more or less what I wanted to say about tensor product representations of SU2. Next Tuesday we will. Okay, that's a little bit more about SU2 that remains.